Well, you see, there's a moment in every scientific story when you pause, take a slow breath, and ask a question that feels almost too bold to speak aloud. And tonight, I want to invite you into one of those moments. Imagine a quiet object drifting through the darkness, an object we once thought came from the deep, cold gulf between the stars. But then, well, as we look closer, we notice shadows that refuse to move, jets that hold themselves perfectly still, even as the body spins, and a path through space that seems to whisper a different origin. And that's the thing, isn't it? What if an object that appears to be foreign, alien even, is actually something born right here within the familiar boundaries of our own solar system? Where would that leave us? What assumptions would crumble first? We build our understanding of the cosmos on these quiet foundations. Interstellar objects move this way, comets behave that way, sunlight scatters in predictable patterns. But every now and then, something drifts across the sky and forces us to rethink the rules. And perhaps, as we follow the faint trail of Three-Eye Atlas, we find ourselves wondering whether we've misread the clues. Could an object shaped by our own cosmic neighborhood still masquerade as an interstellar visitor? Could nature itself be playing a subtle trick on us? Or have we simply overlooked a chapter in the long story of our solar system? Whether it exists at all. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple: to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. Well, when we begin to look at Three-Eye Atlas and the strange, quiet line of darkness that trails across its bright, dusty coma, we find ourselves blinking a little, as if our eyes are trying to adjust to something that should not quite be there. You see, in the world of comets, shadows are supposed to dance. They are supposed to shift with every turn, to fade and reappear as the nucleus spins on its axis. But here, with this object, that shadow lane just sits there, unmoving, like a thin scar cut across a glowing fog. And that stillness sends a little shiver through the scientific instinct, because in a universe built on motion, something unmoving is often the first sign that something deeper, something more puzzling is going on. We know that comets are messy. They tumble, they flare, they shed gas in unpredictable jets. They are sculpted by sunlight and by the restless rotation of their own fractured ice. And, that means a shadow that refuses to drift is already whispering that maybe, just maybe, our basic picture of this object needs to stretch a little. The shadow seems anchored, almost pinned to a fixed geometry, and we have to ask why. A nucleus rotating roughly every 16 hours should smear such a feature into a blur. It should twist it and bend it, but it does not. The line stays sharp, stubborn, unwavering. So, what does that mean? Could the shadow be a trick of perspective? Perhaps a canyon that remains aligned just so as the body spins. But that would require a surface structure so perfectly placed, so uncannily aligned with both the rotation axis and the angle of sunlight, that we drift into the territory of low probability. Not just low, but astonishingly low. And physics tends to frown at coincidences that pile too neatly on top of each other. The way light scatters in a comet's coma is ordinarily chaotic. Dust flees outward, forming a delicate, ever-changing atmosphere around the nucleus. When sunlight hits that haze, it should glow unevenly, flickering in response to every change in density and direction. And if a nucleus rotates, that glowing mist should rotate with it, at least indirectly, because the jets that feed the coma shift, turn, pulse. Yet with 3i Atlas, the coma behaves as if one region is consistently deprived of light, as though something solid and persistent is blocking it. That idea is tantalizing. It suggests order, structure, symmetry. It suggests that maybe this object is not merely a loose clump of ice and dust, but something more, something with a geometry that resists the natural chaos of cometary physics. When astronomers model the scattering of sunlight through a cometary coma, they usually expect variation. It's not just expected, it's guaranteed. But in the images of 3i Atlas, the shadow lane acts with a calmness that borders on eerie. The steadiness of it compels us to consider explanations we might otherwise set aside. Could the nucleus be rotating in such a way that the same face is always presented relative to the sun? That sounds tidy, but it collapses under scrutiny because the spin period is too short, and the observed light curve shows clear modulation consistent with rotation. So the nucleus is turning and the shadow is not. And when something in astronomy refuses to behave, we test natural explanations first. Anisotropic outgassing is often the culprit behind odd cometary features. Gas escaping more vigorously from one side can create what looks like a stable dark lane. But here, the evidence pushes back. The jets in 3i Atlas appear balanced, symmetrical, almost engineered in their alignment. A single stable shadow lane would require gas flow to remain locked in a fixed orientation relative to the nucleus over many rotations. And comets simply do not behave with that level of discipline. Surface morphology is another possibility. Perhaps a deep trench or ridge catches sunlight in just the right pattern. But again, for it to project an unwavering dark streak into the coma, the geometry would have to remain constant through spin cycles and, even small variations in shape should produce flickering, not stillness. The silence of the shadow, its refusal to ripple, becomes almost as interesting as the shadow itself. There is something almost philosophical about this. Time, on a spinning body, is expressed through change. Shadows migrate, brightness shifts, the world turns. We grow older, clocks tick, and so does a comet. But here, the shadow refuses to age. It holds its position as though time is passing for us, but not for it. And that invites a thought that feels strange to even articulate. If a feature resists time on an object defined by motion, maybe we are not reading the source of that feature correctly at all. Scientists are used to probabilities, to the quiet language of likelihood. And when every natural explanation requires a chain of improbable alignments, we are reminded that science is not just about collecting facts, but also about knowing when to pause and re-examine assumptions. Not just what we see, but how we interpret what we see. It's not that the phenomenon breaks the laws of physics. It's that it brushes close to the edges, forcing us to squint and ask whether the laws are being expressed in a way we have not yet imagined. If the shadow lane is real in the physical sense, meaning it is not an artifact of observation, then something about the rotational dynamics of 3I Atlas is deeply unusual. The usual equation of a spinning body emitting dust does not quite apply. We would need a surface configuration that remains identical through rotation, or a direction of outgassing anchored to a fixed point regardless of how the nucleus turns. But dust emission is thermal. It depends on solar heating. It depends on exposure, and exposure changes with spin. So for the shadow to be stable, we would need to consider a model in which either the heating is asymmetrical in a way that never varies, or the dust is being controlled by mechanisms we do not normally associate with natural cometary behavior. That does not mean something artificial. It simply means something unmodeled. And unmodeled phenomena are invitations. They tell us there is more to learn. One of the most perplexing aspects is that despite the rotation, the shadow shows no cyclic modulation. If it were tied to a natural feature, we should see it brighten, disappear, shift slightly, then return as the comet spins. But across observations, it behaves as though rotation is irrelevant. That suggests decoupling. The shadow-producing mechanism is not obeying the rotational frame of the nucleus. And decoupling is rare in small bodies. It usually requires internal processes, complex layering, or some kind of stabilizing mechanism. Comets are fragile, porous. They do not host the kind of rigid structural coherence that could lock a shadow in place regardless of spin. This is why astronomers studying 3I Atlas feel an odd mix of excitement and caution. Excitement because the object challenges established models. Caution because whenever data invites unusual interpretations, we must be careful not to leap too quickly. But even with caution, we have to admit the question is growing louder. Why is the shadow so still? And there is another layer. When an anomaly appears in astronomy, the simplest natural explanation is usually correct. But here, each simple explanation bends under its own weight. Alignment too perfect, rotation too incompatible, scattering too stable. Each feature could be natural, but all together they form a pattern that feels sculpted by forces or events we do not yet understand. I suppose what this leaves us with is a sense of wonder, the kind that makes you lean back a little and imagine the object drifting through sunlight, holding onto its quiet line of darkness as though protecting a secret, not an artificial secret necessarily, but a physical one, a clue to a chapter of cometary physics still unwritten. And as we try to understand how a still shadow can exist on a turning world, we begin to notice that this anomaly does not stand alone. It is only the first of many. Because if the shadow is strange, then the jets will be stranger still. And as we move into that next mystery, the question becomes even more intriguing. How does a comet produce symmetrical, unwavering jets in a universe where chaos is the rule? And as we move from that unmoving shadow into the next mystery, well, we find ourselves staring at something just as strange, perhaps even stranger. Because if a shadow that refuses to drift is already pressing us to rethink the comet's surface, then these jets, these perfectly straight and unwavering jets of gas rushing out from 3I Atlas, are the next quiet contradiction. And you see, in the natural world of comets, jets are supposed to be alive. They twist, they spiral, they pulse with the rhythm of rotation. They are, in a sense, the comet's breath, shaped by heat, by spin, by sunlight. But here the breath is steady, almost deliberate, and that is where our curiosity deepens. When we look at typical comets, say 2I Borisov or the great Cold Wanderer C2017K2, we see jets behaving as nature intends. They flare from hot spots as the sun warms the ice trapped within the nucleus. And as the nucleus spins, these jets curve, weaving through space like threads carried in a slow cosmic breeze. They do not form straight lines that endure across many rotations. They do not sit still. We expect wobble, variability, asymmetry. And yet, 3I Atlas meets none of those expectations. The physics of natural jets begins with heating. One patch of the surface becomes warm enough to sublimate its frozen gases, and that patch puffs out material, forming a jet. As the comet rotates, that patch moves, and the jet should trace a loose spiral. It's not just likely, it's inevitable. So when we look at 3I Atlas and see jets that never twist, that never braid themselves into curves, we feel that familiar tug inside the scientific mind. Something is wrong with our assumptions. Well, perhaps one might say the jet is aligned exactly with the rotation axis. If the axis points toward the sun, then as the comet spins, the jet would appear nearly constant in direction. But this explanation, elegant at first glance, begins to wobble under examination. The rotation axis would need to be pointed with astonishing precision, not just somewhat aligned, but aligned to within a degree or two across days and weeks of motion. And the jet itself would need to originate from a region so perfectly centered that its direction never changes. That kind of fine-tuning is rare in natural systems. Not impossible, but rare in the way that rolling dice 1,000 times and watching them come up the same number is rare. And, well, science is cautious with rare explanations. And there is another layer to this. Even if the jet were aligned with the spin axis, the brightness should still vary. The heating surface would still shift slightly. Microvariations should ripple through the escaping gas. But 3I Atlas behaves almost like a lighthouse beam that never rotates, a column of light locked in place, even though the tower is turning underneath it. That image alone should signal that something unusual is happening. When we compare it to comets like 67 P-Churyumov-Gerasimenko, the one visited by Rosetta, the difference becomes starker. That comet was alive with curls and corkscrews of dust. You could see jets twisting like soft ribbons pulled by invisible fingers. They danced with the nucleus's rotation, each turn leaving a new impression in the surrounding coma. But 3I Atlas does not dance. It stands still. And that stillness, repeated across observation after observation, becomes more puzzling the longer we stare. Natural jets also face the constant influence of solar wind. The sun is always brushing the escaping gases aside, distorting them, bending them into arcs. So, how does 3I Atlas resist that nudge? The jets remain narrow, straight, drawn like lines, with an impossibly steady hand. Something about them suggests a rigidity uncommon in gases escaping through vacuum. A jet, by definition, expands, it widens, but here the jets remain tight, as though constrained by some mechanism we cannot see. One might imagine deeper thermal processes. Perhaps materials beneath the surface form a system of channels that direct the flow upward in a consistent vector. But comets are fragile. They fracture easily. Internal channels should collapse as the body warms. A system robust enough to produce stable jets over multiple rotations would require structural integrity that does not match what we know of cometary interiors. Not just sturdy, but engineered in its sturdiness. And, well, that word engineered is dangerous. We must be careful. We are not claiming design. We are simply acknowledging that the behavior aligns better with systems that maintain shape under stress, unlike the crumbly, stitched together textures of a typical comet. The thermodynamical models, when run with variations of composition, spin, solar heating, and gas pressure, produce jets, yes, but not these jets, not ones that hold a straight line with almost defiant calm. The models show spirals, they show wavering, they show outbursts that wax and wane. For 3i Atlas, the natural simulations require improbable precision. The rotation axis must line up with the jet direction almost perfectly. The active region must be narrowly confined, and the internal structure must permit a constant escape without shifting. The probability shrinks with each added constraint. And the fact that the jets do not twist with rotation, that is perhaps the most telling detail of all. A rotating nucleus sweeps its jet-emitting surface around, and unless the jet is anchored at the exact rotational pole, it cannot maintain its direction. And for 3i Atlas, the light curve suggests a clear rotational period. The nucleus is spinning. It is not a tumbling anomaly. So how can the jets ignore that spin? Think for a moment of a garden sprinkler. If it is anchored at the tip of its axis, the water sprays outward and spins with the body. But if the nozzle somehow stayed locked in place while the body under it rotated, you would begin to wonder what hidden mechanism kept it aligned. That is what these jets feel like. Something steady while the foundation beneath it turns. And in natural systems, steadiness is usually the first hint of complexity. Complexity beyond what first meets the eye. We must also consider symmetry. The jets of 3i Atlas are not just straight, they are paired. They extend in opposite directions with a balance that is difficult to explain. Comets do produce multiple jets, of course, but the symmetry is rarely geometric. It is messy, uncoordinated. The sun warms one side more than the other, cracks open in unpredictable places. The resulting patterns resemble tangled threads, not mirrored structures. But here, the symmetry is clean, almost mathematical. That symmetry carries implications. It suggests either an internal structure that channels gas flow along two opposing exits, or a thermal configuration that keeps 2 points identically heated. But comets rotate, the subsolar point moves, heating shifts. Maintaining identical thermal profiles on opposite sides is like keeping 2 candles burning at exactly the same height in a windstorm. Not impossible, but unlikely. Unlikely enough that we pause. One of the interesting consequences of symmetrical jets is that they can cancel out rotational torque. Normally, jets act like tiny thrusters, altering the spin. But if they are positioned with near-perfect alignment and balance, they produce no net change. And that could explain why the rotation of 3i Atlas does not seem to evolve. But then we face a circular question. For the jets to stay so symmetrical, the rotation must remain stable. For the rotation to remain stable, the jets must remain symmetrical. It's a delicate dance that natural systems rarely perform without stumbling. We begin to get the sense that the jets, like the shadow, point us toward a deeper puzzle. It's not that they break physics. They do not. But they do strain the typical models. They ask us to reconsider the variability of comet surfaces. They ask us to imagine internal temperature gradients that remain locked in position. They ask us to stretch probability beyond where it usually sits comfortably. And when probabilities stretch too thin, scientists start to look for alternate paths. The curious thing about 3i Atlas is that each anomaly could be dismissed on its own. A stable shadow, perhaps an odd geometry, straight jets, maybe a lucky axis alignment. But together they paint a picture that feels coordinated, as though the object is not just reacting to sunlight, but maintaining a posture, a composure in the face of it. The deeper question is whether this composure is natural. Nature is capable of remarkable order, but we usually see that order arise from known processes. Here, the processes feel incomplete, the models stutter, the simulations require parameters that are just a little too perfect. And when nature presents perfection, scientists look twice. As we linger on these jets, we also begin to sense that we have arrived at a threshold, because if the jets resist rotation, then so too might other emissions. If the symmetry persists, then perhaps the internal structure is not what we expect. And if the rotation does not influence the emissions, then the next mystery grows even sharper. How can a rotating object show no rotational signatures in its visual and dynamical behavior? That is where the path bends naturally into the next chapter, because the issue of spin, of a nucleus turning without imprinting its motion onto the very cometary features that should reveal it, invites a deeper and more unsettling question about the decoupling of rotation itself. And as we let that thought settle, as we drift from those strangely steady jets into the deeper puzzle beneath them, well, we find ourselves standing before a question that feels almost philosophical at first glance, because if a comet spins, and 3i Atlas most certainly does, then its rotation should leave fingerprints everywhere. It should tug at the jets. It should smear the shadow. It should dance across the light curve like a heartbeat. But here, the fingerprints are faint, almost erased, as though the motion of the nucleus has been quietly disconnected from the world around it. And that disconnection, that decoupling, is where things begin to feel truly unusual. You see, in comet science, rotation is one of the great shaping forces. It is not just a detail, it's a driver. The nucleus spins, and with every turn, it changes what the sun can see. And as the sun sees new terrain, new pockets of ice warm, and new gas bursts outward, so the coma brightens, dims, shifts, the jets twist. The entire object breathes through rotation. So when we detect a clear rotational period for 3i Atlas, one that seems to fall near 16 hours, but we do not see the normal rotational modulation in its appearance, we pause, and we pause again, because something about that mismatch feels like a whisper, that the surface and the emissions are not speaking the same language. To determine a comet's rotation, astronomers build a light curve, a sort of brightness timeline, and as the nucleus rotates, the amount of reflective surface facing the observer changes. Peaks reveal bright surfaces, troughs reveal darker ones. It's a beautiful method, tried and true. But when the light curve of 3i Atlas tells us the body is rotating, and the coma simultaneously behaves as though the world beneath it is frozen in place, we find ourselves balancing two truths that do not blend easily. The comet spins, and yet the visible signatures of rotation refuse to respond. Perhaps the jets are somehow independent of the nucleus, fed by a reservoir beneath a stable crust, ejecting gas through openings that never shift. But comets do not work that way. They don't have plumbing, they don't have pipes directing material upward. Their interiors are chaotic, fractured, soft. Sublimation happens at the surface. It cannot remain stable in orientation if the surface itself is moving. So that explanation falters. Another possibility is the idea of decoupled emission, that the gas leaving the comet originates from a deeper, insulated chamber that maintains pressure independent of rotation. And, while deep emission has been hypothesized in rare cases, it usually emerges chaotically through vents that open and close. For 3I Atlas to maintain entirely stable jets across multiple rotations, the internal source would need to remain constant and the vents would need to remain precisely oriented. And again, nature resists precision of that degree. Some scientists have suggested internal layering. If the nucleus contains different strata, with some regions capable of insulating colder pockets and others of exposing warmer regions, perhaps the thermal behavior could remain somewhat steady, but that does not solve the core puzzle. The rotation still moves the surface relative to sunlight. Changes should occur. No layering prevents the fundamental fact that spinning a body changes its thermal map. There is also the question of momentum. Jets act like tiny thrusters, pushing gently against the surface that emits them. And over time, they change rotation rates. We've seen this clearly in comets visited by spacecraft. Rotation speeds up, slows down, wobbles. So for 3I Atlas to rotate with such apparent stability, despite steady jets, suggests torque cancellation. That means jets would need to be balanced to extraordinary precision, positioned so symmetrically that every push from one jet is countered by an equal push from the other. And the idea of perfect torque cancellation in a small, naturally fractured object drifts into the improbable once again. We must also consider what the lack of smeared features implies. If the nucleus rotates but the coma does not show evidence of it, then something about the link between surface activity and coma formation is being suppressed, as though the act of rotation is not communicated outward. It's not affecting the dust. It's not bending the jets. It's not softening the edges of the shadow. We grow older, clocks tick, worlds turn, and yet 3I Atlas behaves as though turning does not matter. Perhaps, the surface is unusually smooth, offering no brightness contrasts, but the light curve clearly reveals variation. The nucleus is not uniform. It has brighter and darker regions, it has shape. That means the rotation is real. But then why does the coma ignore it? Some have suggested that the coma might be too dense, masking variations. But the observations from different instruments, different filters, different observation windows do not support this. The coma is present, yes, but not thick enough to hide rotational signatures entirely. And even if it were, the jets should reveal the turning motion in their curvature. They do not. So we are left with an uncanny possibility. The rotation of the nucleus and the behavior of the emissions seem partially disconnected. The nucleus moves, the emissions do not respond. It's not a violation of physics, but it is a strain on our models of comet behavior. It suggests a surface that is not behaving as a source of emissions in the usual way. It suggests internal dynamics that do not match the typical thermal evolution of small icy bodies. It suggests a degree of stability that natural objects normally do not maintain under solar heating. And, well, this is the point where the scientific mind becomes both cautious and excited. Cautious because such anomalies can lead us astray if we leap too quickly to exotic explanations. Excited because anomalies often mark the edge of new understanding, that place where the map of current knowledge begins to crumble and fall away, revealing something richer underneath. We can imagine, just for a moment, an object whose internal structure resists external influence. A nucleus whose emissions emerge not from rapidly changing hotspots, but from self-regulating vents that maintain alignment regardless of rotation. It's not impossible, it's just unusual. And the universe is full of unusual things, but unusual things often come with signatures, heat irregularities, changes in spin, detectable asymmetries. 3i Atlas, at least from the data we possess, refuses to play by those rules. There is also the question of feedback. In natural systems, forces act on one another. A jet influences rotation. Rotation influences jet direction. It's a loop. For 3i Atlas, to maintain emissions that ignore rotation, that loop must be broken or altered, and the breaking of a loop in a physical system often signals an underlying stabilizing mechanism, something acting as a buffer, something regulating rather than reacting. But comets have no known mechanisms for regulation. They do not have feedback systems. They simply respond to heating, fracturing wherever internal pressure grows too high. So why does 3i Atlas not behave like that? Why does it not show the expected irregularities? Why does its rotation seem to float behind a curtain, disconnected from everything its body emits? In some models, researchers have explored the idea of internal voids, hollow regions, where gas pressure might accumulate without immediately reaching the surface. If such voids exist in just the right geometry, one could imagine gas escaping through narrow vents that, by chance, line up perfectly and resist rotational modulation. But for this to remain steady over time, the internal void must maintain constant pressure, the vents must resist change, and the heating must remain delicately balanced. Comets are fragile things. Their vents collapse, their voids shift. Maintaining a constant configuration is difficult. And if the emission is indeed partially decoupled, then it would also explain the persistence of symmetrical jets. But it raises the stakes for the puzzle. Because a system stable enough to maintain symmetry over many rotations is also stable enough to question. Stable systems invite hypotheses of structure. Structure invites hypotheses of origins. And in a world where comets are expected to be messy, the emergence of structure is a clue that deserves attention. The deeper we follow this thread, the more we sense the object resisting our standard categories. It's not behaving like a typical comet. It's not evolving like one. It's not responding to sunlight in the expected ways. And this leads us to the next, perhaps even more consequential puzzle, its path through space. Because if rotation does not quite match emission, and emission does not quite match expectations, then the trajectory of 3i Atlas begins to raise questions that are just as fundamental. And the orbit itself, hyperbolic at first glance, may not be entirely what it seems. And as we step gently from the puzzle of rotation into the question of motion itself, well, we find the story of 3i Atlas widening again, almost as though the object is quietly inviting us to look not just at its body, but at its path through space. Because if the rotation behaves strangely, and if the emissions behave strangely, then the orbit, this long, sweeping curve that first made astronomers whisper, Interstellar begins to feel like the third piece in a chain of mysteries. And it is here, in the mathematics of trajectory and the subtle push and pull of forces, that the object reveals yet another layer of strangeness. When 3I Atlas was first observed, its orbit appeared hyperbolic, and in astronomy, a hyperbolic orbit is a big statement. It means the object is not gravitationally bound to the Sunday. It comes in once, it leaves forever. So with eccentricity greater than 1, we tend to place such bodies in the category of interstellar visitors, like Oumuamua or 2I Borisov. It's not a guess, it's a rule of motion. If the path curves too widely, too loosely, then no gravitational handshake binds it to our star. But then, as we watched more closely, things began to shift. The direction of the non-gravitational acceleration, this tiny extra push on the comet, remained steady, unnervingly steady. Comets often exhibit non-gravitational acceleration because jets push them unevenly, but those pushes vary, they flicker. They change with rotation and solar heating. 3I Atlas, however, showed acceleration that was not just gentle, but stable in both magnitude and direction. And, that stability is as odd as the straight jets and unmoving shadow. It suggests a force acting more like a constant wind than a sputtering breath. The interesting part is that when astronomers began modeling the orbit with that stable acceleration included, the eccentricity shifted. It dropped. Not much at first, but enough to raise the question, what if the orbit is not truly hyperbolic? What if the path that looked interstellar is actually shaped by a consistent outward push that mimics an interstellar trajectory? The idea is subtle but profound. If you add even a small, steady force in the right direction over months, the orbit can appear more open than it truly is. A bound path can masquerade as an unbound one. This leads naturally to the question of origin. If 3I Atlas is not truly interstellar, then where could it have come from? And the solar system is full of reservoirs for icy bodies. The Oort cloud stretches like a vast, invisible halo around us, sending comets inward from time to time. The scattered disk holds bodies perturbed by Neptune's gravity. And the physics of long-term orbital evolution allows for objects to slowly drift, pushed by jetting over thousands of years, into what looks like a hyperbolic trajectory, even if they remain technically bound. That idea, challenges a sacred assumption. We have grown accustomed to treating hyperbolic objects as travelers from other stars. It's clean, it's simple, it fits the mathematics, but nature seldom adheres to our need for simplicity. And, 3I Atlas presents a case where simplicity may mask a more complicated truth. The stable acceleration hints that the apparent eccentricity may not reflect true origin, but accumulated behavior. To understand how such misinterpretation might happen, we need to think about how small bodies move. They are light, they are porous, their jets act like miniature thrusters. Over time, these thrusters can reshape orbits, gently but meaningfully. And if the jets are steady as they appear to be in 3I Atlas, the direction of the extra force would be predictable enough to shift the orbit in a consistent fashion. In most comets, chaos dominates. Jets turn on and off. Direction changes. Accelerations wobble. So their paths, though influenced by jets, remain identifiably bound or unbound. But with 3I Atlas, the steady direction means the acceleration acts almost like an additional constant term in the orbital equation. And constant forces accumulate elegantly. They can lower eccentricity, they can raise it, they can push the comet outward in a way that mimics a hyperbolic escape. When researchers rewound the orbit of 3I Atlas using models that included this smooth acceleration, they found that the path did not diverge dramatically into interstellar space, but rather curved gently backward toward a long period origin. It nudged us toward the idea that the comet may have been visiting the inner solar system before, long before, perhaps in epochs when humans did not yet carve stories into stone. And then comes the question of the Oort cloud. This distant reservoir of icy bodies is vast, so vast that calling it a cloud is almost poetic rather than literal. If 3I Atlas came from the Oort cloud, it would fit the rough profile of a long-period comet, but the cloud's bodies are ordinarily perturbed inward by galactic tides or passing stars. Their orbits, while long, are still bound, and they rarely exhibit the kind of stable jets needed to mimic a hyperbolic path. So the object sits in a peculiar space. It behaves like something from the Oort cloud in appearance and composition, perhaps. But its motion behaves like something influenced by a steady, controlled force. One might ask whether the influence of outgassing alone can explain this. And to some extent, yes. A steady jet can produce steady acceleration, but we return again and again to the question of probability. It's not impossible, but improbable. And in science, improbable events require not dismissal, but scrutiny. The scattered disk offers another possibility. Bodies in that region experience gravitational nudges from Neptune and other outer planets, and over long spans, these nudges can launch them into stretched orbits. If 3I Atlas had wandered near a gravitational boundary at just the right moment, its trajectory might have elongated dramatically. And if that was followed by years of steady jetting, the path could widen further still. It's not that the object must be from inside the solar system. It's simply that the door is not closed. The orbit alone does not force an interstellar origin. In fact, when the acceleration is accounted for, the case for interstellar origin weakens. This doesn't resolve the mystery. Instead, it shifts it inward. It asks us to look closer to home, not outward to the stars. And this has implications. If 3I Atlas is from the solar system, then its unusual rotational and emission behavior are features of a local object, not an alien one. That carries weight. It suggests we may be missing a category, a family, or a type of behavior that occurs domestically, quietly, rarely, but real nonetheless. And, well, if the hyperbolic appearance can be explained with physics, we already know, though in an unusual configuration, then the orbit stops being the final word on the object's origin and instead becomes another clue, another puzzle piece fitting into the larger mosaic of anomalies. The steady jets, the unmoving shadow, the decoupling of rotation, and now the possibly misunderstood orbit all lean in the same direction, not toward certainty, but toward possibility. The possibility that 3I Atlas is something shaped within the gravitational boundaries of our own star, not a visitor from afar, but a wanderer whose long journey has twisted into something that looks exotic when we first glance at it from afar. Even more intriguing is the thought that if the acceleration is not just steady but unusually steady, it may reflect an internal mechanism we do not fully understand. A mechanism that could have been operating for centuries. And if such mechanisms exist in some rare comets, then our orbital models for long period bodies may need revision, we would need to account for steady, long-term acceleration in a subset of objects. That idea alone is enough to send dynamicists back to their simulation software. We grow older, clocks tick, and orbits evolve under the accumulation of tiny, patient forces. If 3I Atlas has been pushed for hundreds or thousands of years by jets that behave with unusual consistency, then its orbit may simply be the product of ancient, persistent asymmetry, a shadow of long-forgotten thermal processes repeating themselves with remarkable discipline. And as we take all this in, a quiet question emerges. It's not whether the orbit is interstellar or bound. It's not even whether the jets are natural or unusual. The deeper question becomes, how can an object maintain such steady behavior across time? What internal structure or external influence could sculpt its journey so precisely? And that question nudges us gently, almost inevitably, toward a more speculative horizon. Not a conclusion, but the next mystery one that asks whether deep within our solar system's coldest regions, structures or systems could exist that shape comets in ways we have not yet imagined, and perhaps even raise the faintest whisper of something more deliberate. And as we let that last idea hover there for a moment, we feel the story of 3I Atlas drifting toward a threshold that is both scientific and strangely human. Because when an object resists every familiar category, when the jets are too steady, when the rotation is too quiet, when the orbit pretends to be interstellar but may not be, the mind does what minds have always done under the silent pressure of mystery. It begins to wonder, not to conclude, not to declare, but to wonder. And that wondering leads us into a landscape that feels both unsettling and beautiful. The question of whether deep in the cold outer reaches of our own solar system, something ancient could have existed. Not just ice and dust, but perhaps something capable of shaping an object in ways that nature only rarely, if ever, manages. You see, scientists are careful. They walk slowly around extraordinary ideas. And, this is an extraordinary idea. The possibility, not the claim, not the assertion, but the possibility that 3I Atlas might, in some hypothetical past, have been shaped or influenced by something more structured than ice fractures and sunlight. And if such a possibility exists even faintly, we must approach it with respect, not with eagerness, not with sensationalism, but with that quiet humility that science demands when it steps beyond the well-lit areas of knowledge. What would it even mean for a civilization to have existed in the cold outskirts of the solar system? The temperatures there float around 40 to 60 Kelvin, so cold that chemistry slows to a crawl. Life as we know it struggles to do anything at all. And yet, our understanding of life is built entirely on one example, Earth. It's not out there. It's in here, in the narrow corridor of our experience. So when we imagine what could arise in the deep dark, we must hold our imaginations gently, aware of the limits of what we know. Perhaps such a civilization, if it existed at all, whether it exists at all, would not look like us. It would not walk or breathe or build in ways we understand. It might not leave ruins or signals or lights. In a place where energy is scarce, intelligence would adapt around scarcity, not just physically, but conceptually. Perhaps it would learn to store heat the way we store memories. Perhaps it would shape materials that respond to minimal energy. Perhaps structures could form that look to us like natural objects because they rely on natural forces for stability. But before we drift too far ahead, we must return to the core of the scientific puzzle. 3I Atlas does not show evidence of technology. There are no radio signatures, no geometric plates, no unnatural spectra. And Brian Cox, if he were here in the room with us, would probably smile softly and remind us that science cannot declare something extraordinary without evidence that is equally extraordinary. So this chapter is not about claiming ancient machines drifting through the void. It is about asking whether the anomalies of 3I Atlas, taken together, justify entertaining the idea that we may be underestimating what natural physics in extreme environments can produce, or perhaps exploring whether past civilizations, if any existed, might have influenced objects in ways that have since eroded beyond recognition. The first question, the scientific one, is simple. Could a natural process create an object that mimics design? And the answer is yes. Nature is full of patterns, so precise they look deliberate: snowflakes, viral shells, the geometry of radial area. And in the vacuum of interplanetary space, with billions of years to work, who knows what forms might arise through interactions of heat, spin, pressure, and fracture. That possibility must sit at the center of our reasoning. But the second question, the more imaginative one, lingers. What if, just what if, some ancient process, biological or technological, one shapes something in the outer darkness? Not a spaceship, not a probe, nothing so dramatic, but perhaps a material engineered to endure cold, to preserve information, to drift for eons. If such a material eroded over millions of years, it might look like a comet. It might behave strangely under sunlight. And, it might produce structures, straight jets, stable shadows, quiet rotations that echo design without revealing purpose. Yet we must remind ourselves always, there is no evidence that 3I Atlas is artificial. None. It's not that we see something artificial and fail to interpret it. It's that we see something natural and fail to fully understand it. That distinction matters. It protects science from wandering too far into illusion, even while allowing wonder to breathe. So then, if not civilization, what about a more subtle idea? That ancient chemistry, not life, not machines, but a prebiotic or quasi-biological system might have existed in the cold. We often think life needs warmth, but some chemists suggest that extreme cold preserves complexity. It slows the chaos of reactions, allowing fragile structures to survive longer. And in the slow, deep freeze of the Oort cloud, conditions might allow for forms of order that we have not yet imagined. Perhaps 3I Atlas carries traces of such a system, patterns in its structure that resist heat just long enough to create stable behaviors under solar warming. Not intelligence, not intention, but resilience, a kind of frozen logic. And if that were true, or even partly true, then our models of cometary behavior would need to expand. Not just in terms of physics, but in terms of what structures can persist beyond the reach of planetary influence. Yet even this idea, subtle as it is, must be held lightly. We return again to the guiding principle. Anomalies do not prove extraordinary origins. They simply point toward areas where our understanding is thin. And in science, thin understanding is an invitation, not a conclusion. Still, the idea of an ancient civilization remains as a poetic question, even if not a scientific one. Could intelligence once have bloomed in the dark outskirts, in the long quiet around our sun? Could something have risen and fallen leaving behind only the faintest whispers in the form of a strange trajectory or an unusually stable jet. We do not know, and perhaps we will never know, but the very act of asking humbles us. It reminds us that the solar system is vast enough to hold secrets older than our species. It's not that 3i Atlas must be artificial. It's that its behavior nudges open a door in the mind, a door that leads to deeper questions about what can exist, what has existed, what might exist still. And this is where science and wonder meet. In 2025, or in 10,000 years, the rules of inquiry remain the same. We ask, we test, we refine, we imagine. The role of evidence is absolute, the room for imagination is infinite. And as we balance those two forces, we find ourselves preparing to step into the next chapter of the mystery. Because if the shadow, the jets, the spin, and the orbit all challenge us, then what comes next is the quiet heart of the scientific method, returning to the data itself, spectra, radiation, thermal signatures, to ask what we have overlooked, and to let the universe reveal, in its own time, the next piece of the puzzle. And as we step gently from that speculative horizon, into the quieter light of reflection, the story of 3i Atlas begins to settle into something far more human than alien. Because after walking through the strange shadow that does not move, the jets that do not twist, the rotation that does not announce itself, the orbit that may not be what it claims, and the faint whispers of ancient possibilities, we arrive at a place where science always arrives, a place of questions. And perhaps that is the most important truth of all, not the answers we strain toward, but the questions themselves, widening like ripples through the dark. When you gather all the anomalies together, the unmoving shadow line, the symmetrical jets, the steady non-gravitational push, the rotation that seems to hum quietly beneath a motionless exterior, they form a tapestry that is not just strange, but beautifully strange. And, it is here that the spirit of inquiry deepens, because science is not a machine for producing certainties. It is a lantern we hold out into the unknown, letting each flicker of illumination guide the next step. And 3i Atlas, with all its contradictions, is very much one of those flickers. If the shadow truly stays fixed, if the jets are truly aligned beyond what chaotic nature usually allows, if the rotation is truly decoupled from the emissions, then we must admit that something in our understanding of small icy bodies is incomplete. It's not that 3i Atlas must be unnatural, it's that our natural models must stretch. And the stretching of a model, like the stretching of a mind, is what science is built upon. We grow older, clocks tick, and the solar system continues to offer little puzzles that remind us how young we are as observers. 3i Atlas may simply be another such reminder, an object nudging us deeper into the physics of icy bodies, into the complexities of sublimation, into the long timescales where gentle forces sculpt grand illusions. And yet the beauty of this story lies not just in the physics, but in the humility it demands. Even in 2025, with spacecraft sailing past moons and telescopes, peering into the birthplaces of stars, we still stand small before a single wandering object that refuses to behave. And that refusal is a gift. It tells us that the universe is still unsolved, still unpolished, still capable of making even the most experienced astronomer blink and murmur, well, that's odd. As we look toward the future, we see the tools that will help us peel away the layers of this mystery. Radiation data may reveal subtle thermal behaviors. Spectral measurements might show whether the composition of 3i Atlas differs from typical comets in small but important ways. Next generation orbital models may incorporate steady acceleration into their predictions, showing whether the hyperbolic illusion dissolves under more refined calculations. Each dataset becomes a thread, and we pull gently, carefully, knowing that some threads will unravel confusion, while others will unravel understanding. And the significance of all this, the deep, gentle significance, is that if 3i Atlas truly came from within our solar system, then we are forced to confront a simple, humbling idea that we live in a neighborhood far less familiar than we pretend. It's not out there. It's in here, in the darkness, beyond Neptune, in the icy realm where time is slow and silence is long, that our ignorance gathers like frost. If 3i Atlas is a native wanderer rather than an interstellar visitor, then the first chapter in the story of our solar system may need rewriting, not just with new data, but with new imagination. And that rewriting is not a burden, it is a privilege. It means the universe still trusts us with surprises, still whispers to us across the void, still teaches. But perhaps the most inspiring part of this entire journey is that the anomalies remain open. They remain questions rather than verdicts. Science thrives on such questions. They are invitations, not frustrations. They tell us that knowledge is not a closed circle, but a spiral, widening each time we return to a mystery with sharper tools and softer assumptions. What does it mean that a shadow does not move? What does it mean that jets remain symmetrical? What does it mean that rotation fails to express itself in the coma? What does it mean that a hyperbolic orbit may not be hyperbolic at all? These are not just scientific queries, but philosophical ones. They ask us to examine the fragile boundary between what we believe and what we observe, between the tidy patterns we expect and the unruly truths that drift toward us on long, cold trajectories. And, well, as we stand here, poised between wonder and caution, we feel the story leaning forward again. Because the next step in this mystery is not to leap toward extraordinary explanations or retreat into ordinary ones, but to look more deeply into the data, into the physics, into the quiet spaces where anomalies hide. The next chapter in the life of 3i Atlas will be written by future observations, by radio telescopes measuring its outgassing with higher precision, by spectrographs capturing the faint fingerprints of its materials, by dynamicists refining models that stretch across decades. And each of these tools will push gently at the boundaries of what we know. So when we pause now, taking a breath in the calm after so many questions, we find that the story is not ending at all. It is opening, it is widening, it is unfolding toward whatever discoveries wait in the shadowed regions of our own celestial home. And realizing that perhaps the next steps are not just about 3i Atlas, but about the way we listen to the subtle clues in the night sky. And as we turn our attention toward what comes next, toward those deeper observations, those quieter signatures, those delicate threads of radiation and spectrum, we begin to sense the faint outline of the next great question forming just ahead, waiting patiently for us to notice it.